All right, so we were discussing some of the basic statements in ADS-CFT yesterday. I want to move on from there to telling you some more elements of the dictionary today. But before I do that, do people have questions? No? All right, so let's just reorient ourselves. And talk about the dictionary between the objects on the two sides. So we've seen that classical fields in ADS map to quantum operators in the field theory. And the field sort of does double duty. There's a piece of the field which is the classical source you would turn on for the operator, and there's a piece of the field that corresponds to being the operator itself. So I think I'll use the same notation I used yesterday, but now this can be any collection of fields. Phi is sort of goes like and this is the source, and this is the expectation value or the vacuum expectation value in the presence of the source. No, now I want to make this statement quite generally. Okay, so the statement is true for any classical field. I gave you the mapping explicitly for scalar fields, but you could do it for any higher spin. It's just that writing down the analogous classical equation just gets a bit more messy. But if you have Maxwell equation, there would be a similar statement for the Maxwell vector potential. If you wrote down the spin 2 wave equation, similar statement for and so on and so forth. Okay, but the message I want to take away is that for any set of classical fields in ADS, there's a corresponding operator, and you can extract the data for that operator from the behavior of the field near infinity. Okay. So since I was asked, let me write this as for some vector field. I will have use my notation from yesterday. Let me call this A mu plus J mu. I had this funny notation which I should have explained. Okay, so that's a set of statements, at least for the fields I will be mostly interested in. So this is for scalars. I want it to be abstract, but maybe it's not. It's worth writing it out explicitly. This is for massless vectors, Maxwell fields, and this is for metric. And my notation is that I will use capital letters to indicate indices in the bulk in ADS. And I'll use Greek lowercase to to indicate boundary indices. Okay. Just to keep things a bit more clear. So M and N run over all the x's which include time, and z, mu and nu rest run over the x's. All right, so this is fallout for the various fields. I haven't told you how you get them, but if you write down the spin 2 equation, you will see that the matrix does this. In fact, if you just study the asymptotics of Einstein's equations, you'll see this, as I'll come to in a second. And if you study the Maxwell equation, you'll see this. Okay, so we have a dictionary between these basically. Given any quantum operator, you can sort of engineer a field in a bulk that would sort of do the job. And the way the story goes, initially, at least ADS-CFT was invented by thinking about particular field theories that came out of string theory, right? Like L equals for super Yang-Mills. Mallasena was interested in studying the physics of D3 branes, and the world volume theory of D3 branes is a very particular quantum field theory. So if I tell you this, if you look at string theory on ADS5 cross S5, in the semi-classical limit, we have LADS being much larger than L string, being much larger than L Planck, or equivalently, this is n equals 4 super Yang-Mills in 4 dimensions with gauge group SUN. Yeah.
It's crucial to have the string length that is much bigger than Planck length.
Okay. So if the string length is order the Planck length, then the string coupling is order 1. Okay. String theory has 2 parameters, right? It has a string scale, which sets the tension of the string, and what you've been doing in light-cone quantization is you've been studying the theory at the tree level. You've been studying the spectrum of the light-cone string. But strings interact, right? And the strength of those interactions is G-string. So if you want to do perturbative string theory, you want to keep G-string small. Okay? If you don't keep G-string small, then you have to worry about what the non-perturbative theory is. Yes. So the hierarchy there is ensuring that we can actually do this. It has this hierarchy has a meaning here, which I was just about to write down. So what this means is that here I need n much bigger than 1, which is coming from L string being much bigger than L Planck. And I want this coupling, which is Yang-Mills coupling squared times n, to be also much bigger than 1. And this comes from LAD as being much bigger than L string. Suppose we were at small n. Suppose you wanted to do SU2 n equals 4 super Yang-Mills. You certainly can do SU2 n equals 4 super Yang-Mills. But one thing I haven't tried telling you is that the large n limit of the theory simplifies quite a bit. So maybe I should go back and tell you in a second. And to ensure that happens, I need this hierarchy between string and Planck length. If you don't do that, from the bulk theory, it's clear what happens. From the bulk theory, you cannot suppress string loop effects. So you have to actually do quantum string theory. Okay? So you lose. So my philosophy is the following: these two theories are equivalent at the quantum level, completely equivalent at the quantum level. We haven't defined this theory fully at the quantum level. If you can define it, you will see that it's the same as this theory at the quantum level. And once you have the quantum theory, you can study it for any values of these parameters. You could study it for L8 as being the same order as L string being the same order as L Planck, right? So that theory we could study, but we don't want to do that because we don't know how to do it. We know how to do semi-classical gravity. So semi-classical gravity requires this, and allowing yourself not to have to include string loop effects requires all these. On top of that, requires these criteria. Okay. So let me come back and tell you so you see, there's something funny. I'm telling you here that I have a strongly coupled theory with a very large gauge group, and the theory is behaving classically, if in the right variables. Right? That's the statement here, because this statement says that you can forget about all of the complications of string theory, and you can just study gravity coupled to a bunch of fields. Yeah, maybe supergravity, but this is the classical theory. And the reason for that is the following. So the large n limit of gauge theories is a classical limit. Okay. And there's a very, very, very easy way to say this. And this was one of the things I was going to explain now. So let's look at the Young-Mills action. Okay, so n equals for super Young-Mills is some gauge theory. It starts out having a kinetic term for the gauge bosons, and then it has various other fields. It has adjoint valued scalars, it has adjoint valued Weil fermions, etc., etc. The details won't matter, but the classical Lagrangian starts out its life as trace of f squared. Okay. Now, the trace here is important because f is an adjoint valued matrix. It carries SUN charges. So you need a singlet under SUN to write down a Lagrangian. Singlet is what is gauge invariant. Right? So, but now I have to worry about how to normalize these traces. And there's a nice way to normalize these traces by declaring that what you have okay, is to get the trace, get factors of n out, because each time you trace so the trace of a matrix right? So we have to trace over the adjoint matrices, and you get an extra you get a factor of n each time you trace. Yeah. A and B runs in the adjoint. So sorry. A and B run from 1 to n. 1 to n. It's an adjoint matrix. So yeah. So actually, it's nicer to write this trace really. If you write it out correctly, I normalize the trace by an explicit factor of n here, so that you can account for the n counting much more easily. So now I'm just going to do one simple thing. I'm just going to count factors of n. I'm going to forget about all the dynamics of the theory. I'm going to count factors of n in Feynman groups. Okay, so so from this trace f squared gives you a propagator plus vertices for the gauge bosons. And the propagator you'd usually write as follows, because f is, I hope this was obvious to everybody, it's non-abelian. F mu nu is its antisymmetric derivative on A, and then the commutator term. So we have a 2-point function from the usual kinetic term from the d mu m nu piece. We have a 3-point function from when you expand out the square from this term times this term, and you have a 4-point function from the commutator square. So let's now try to study how these things will behave. And what I want to do is I want to keep track. So this just says I have a matrix AB coming in. I have a matrix AB going out, because if I put A prime B prime, this propagator is proportional to delta A prime, delta B prime. Yeah, the color indices have to flow through the diagram. So I want to do that a bit more explicitly, and so let me introduce a nice notation that was first proposed by Toft. Which is, let me write out the flow of the adjoint indices by drawing the propagator as follows. So this is proportional to delta AC, delta BT. So this is the same as the single line propagator. I just think of the indices separately. Or if you like, you could think of the adjoint matrix as being composed of a quark anti-quark like object, two fundamentals, a fundamental anti-fundamental, because the tensor product of fundamental anti-fundamental has a adjoint, and track those indices. Okay, but for now this is just a mathematical trick for us to keep track of what's happening. Then I can draw the 3-point vertex as well. Every line is doubled. And then you follow the arrows to get the flow of the color. And there's a 4-point vertex. And look, the way I have normalized the trace with the action here, this guy is proportional to G Yang-Mills squared. So do I want to rescale factors? That's fine. Okay. And now the Toft's insight was the following. So you want to compute any physical correlation function. Or the partition function, or the free energy of the theory. Should admit a series expansion in Yang-Mills squared, and should have factors of n. From traces, or what I will call index loops, because if I try to compute the self energy of the gluons, the one loop self energy would draw by just taking the propagator and gluing it back onto itself. But in my notation, that gluing back comes with this two lines, right? So I have two indices, A and B, and they're sort of glued along themselves. So the n values of A, the n values of B. So this diagram, if I forget about the factor of G Yang-Mills squared, this diagram is proportional to n squared. Right? Just from summing over the A and B indices. There's a two-loop answer. Let's look at the two-loop questions. Here's one diagram. Right, which comes from, so this was just this picture, usual picture. This is this diagram. But this guy, I will leave it for you to count, is proportional to, it's proportional to the coupling. I will introduce this lambda in a second, times n squared. So lambda, what I want to do is I want to introduce a new parameter lambda, which is G Yang-Mills squared n. To get the lambda counting right, you have to take into account the fact that with my normalization, the propagator has 1 over G squared. But there's one more two-loop diagram where the index loops do the following. Okay, this is, so there's an outer loop like this, but the inner loop comes here, goes back, and then it sort of joins back behind this picture. Okay. So distinction between these two diagrams is how the indices are contracted, and I'm not sure you can see my drawing very well, but So here the indices are contracted, it's obvious to see where they're contracted. But here, this leg is going down, and it's coming from behind the board to the top. Okay? So this diagram I have drawn on the plane. So this diagram is a planar diagram. And you clearly see that I can't draw this diagram on the plane because I need to go behind the front to get here. This is a non-planar diagram. They both are two-loop diagrams, so they both have a factor of lambda. That's fine. The powers of G Young Mills squared, if you count them in terms of lambda, they both work out this way. But this diagram has a fewer number of contractions of indices. There's this loop, if you follow, this index loop is the same loop that goes around. Whereas here there are 3 index loops, the 3 sums on n. Whereas here there's only 1 sum on n, effectively. So this diagram is proportional to lambda times n to the 0. Which means that even though these two diagrams will appear at the same order in G Young Mills squared, when we switch to this lambda parameter, they are proportional to lambda, but with different powers of n. Okay? And what Toft realized is that the free energy should be written as a double sum of Sure.
You wrote inverses on your G Young Mills over.
Yes, I did.
So they should be inverse.
No, propagators also have inverses. Sorry, propagator has G Young Mills squared. Yeah. See, where was my Lagrangian? It was 1 over G Young Mills squared. Trace F squared. Propagator has G Young Mills squared. The vertices have 1 over G Young Mills squared. Factors cancel out when I get them right. How do we get n equals 0? So here you see, so let's do the counting. So there's one factor of n from the, there's an n cubed, right? That is clear. And then there are 3 factors of, there's 2 propagators. So I have absorbed the G Young Mills squared I get, and the vertices. So this is really G Young Mills squared n cubed. Okay. So this I'm saying is G Young Mills squared n. So I have to explain to you where I get an n from. Okay. So my statement is the following: follow this line. This line is coming, it goes back, comes down here, it flows this way, comes back here, goes back. So there's only one line. Yeah. So, yeah.
Since the beginning we write the propagator and vertices propagation bottoms, I didn't really understand why are we writing two color indices on each side if each spaghetti should only be carried one.
So
Probably very
it's a quark has single color index. A gluon has two color indices. Gluon is in the adjoint, right? So an adjoint matrix has two indices. Yeah. The easier way to think about it is an adjoint is roughly like a meson. It's like a quark antiquark. Bad analogy, but if you want to just do the counting, you can get it from there. So Toph's intuition was that you should be able to write the answer as a sum over some you should be able to take the free energy, for example, and write it as some function of lambda times some power of n. And the function of lambda, of course, so usually you would have said that the free energy or whatever quantity we're computing is some asymptotic series in the coupling, because we're doing perturbation theory with some various loops, and we get some answer which depends on the coupling. And what he said was, yes, that's true, but it's better to switch from the coupling G Yang-Mills to lambda so that you can get a function of lambda that's sort of natural from perturbation theory point of view, but it comes weighted with powers of n. And this weighting with powers of n allows you to distinguish planar and non-planar diagrams. Okay? So let me do for you a full counting and show you that actually it's a very powerful statement. We've just done simple Feynman diagrammatics, but you'll see some remarkable statement coming out of this. So let me write my Lagrangian as n over lambda trace f squared plus dot dot dot, and use the fact that propagators behave like lambda over n, interaction vertices scale like n over lambda, and every loop gives me a factor of n. So I'm not going to evaluate any Feynman diagram. I'm just going to count powers of lambdas and n's that come up in Feynman diagrammatics. So draw a Feynman diagram. Take any Feynman diagram. Let's say this one. Get some. I've just used the double line notation to draw it as some kind of piece of Swiss cheese that you can see. And the thing you can figure out is that these planar diagrams are diagrams, since you can draw them on the plane, you can stereographically project the plane and think of them as diagrams drawn on the sphere. Right? And you see that if you think of this, and you can imagine that what you should be doing is you can sort of think of these diagrams. You can look at the center of these loops and imagine that there's a graph which triangulates the sphere. So you take the sphere, you draw this diagram on the sphere, and then you sort of think of breaking up the sphere into little triangles. And for this picture with the triangulation, you can make the following observations: that the vertices map to vertices of the Feynman diagram, are vertices of the graph. or triangulation. The propagators are edges of this graph, and the loops are faces. Okay? See, now we have everything. We know for a given diagram, all I need to tell you is how many vertices, edges, and faces I have. And you know the powers of n and lambda that come from every one of them. Okay? So random diagram, so powers of lambda comma n for random graph are simply n over v, n over lambda to the power v, where v or vertices, lambda over n to the power edges, and n to the power of number of faces. This is the power of, so this could be some physical quantity we're computing, so this could say be the free energy. Yeah, it of course depends on, you know, if you are computing correlation function, it will depend, there will be some function of positions of operator insertions and so on and so forth. But I don't care about all those details. I'm just asking, you want to compute some physical process, write down that Feynman diagram, and all I'm telling you is without doing any work, we can at least pull out the factors of these guys. So we can see how perturbation theory is organized. And you see now, so total power of n is nice. So I'll abbreviate vertices, edges, and faces to V, E, and F. And I get lambda to the E minus V. Good. Now, I hope everybody knows the famous result in 2 dimensions, that for a graph, vertices minus edges plus faces is an invariant, is the Euler character. So this just tells you the number of handles that you have. That gives you the genus of the surface on which you can draw the graph. Is a topologically invariant. So the statement here is very simple. While we started doing perturbation theory the standard way, you see that perturbation theory wants to be reorganized. It wants to be reorganized based on powers of n determined by the Euler character of the surface on which you can draw the Feynman graph. So I'll call this in the 't expansion n large with lambda, which is g squared, n fixed, are determined by Euler character of the surface on which we draw the graph. Do people know how to prove the formula for the topological invariance of the V minus E plus F? Okay. So you can, of course, draw simple graphs and check, but here's what I've heard described as physicist proof. It's a very great proof told to me by my friend. So imagine you take a Riemann surface and you lay down some random electric circuit on that Riemann surface. Just take a Riemann surface and take wires and just connect up wires with nodes on that Riemann surface. So take two external leads and stick them on two nodes of this network and set up a current flow on this Riemann surface graph, on this network that I've drawn on the Riemann surface. So what we know physically is that there's guaranteed to be a unique current flow pattern on this graph, on this set of wires that make up the graph. Right? Now there's a very simple principle that when there's a unique answer to a physical problem, it means that number of variables and the number of constraints must match exactly. So what are the variables and what are the constraints? The variables are the currents flowing through each leg of the graph. And the number of constraints are the constraints that come from, I hope you've heard this word, Kirchhoff's laws, which tell you about current conservation at vertices, that if you have a current coming in and currents going out, they must add up. And there's current conservation on the loops. So write down the total number of constraints you get, which are again given in terms of edges and faces. Total number of constraints you get from the vertices. The unique solution. They must match. That's the answer. Okay. Of course, mathematicians would prove this a bit more rigorously, but if you want to be convinced that it works, it works. Right. So this was Stokes' insight, but you see what this says is perturbation theory in this 12th limit is reorganized as a genus expansion. So, say the free energy takes the form n squared times some function of lambda. Sure. I'll keep going.
That sounded nice, what you said about physics proof.
Yeah.
But how do the handles of the Riemann surface enter into this picture? Because when I thought about it...
Oh, I don't know. I was proving that this is an invariant. Okay. To go from here to here, I need to tell you some more. Why are the handles? Okay. Why is this quantity in terms of the handles? Yeah.
So that is invariant for...
Correct. So on what this statement is saying is that you take the sphere, you draw all the Feynman diagrams you can draw on the sphere, and do the lambda perturbation theory on that. You'll get some function f0 of lambda. You take the torus, you do the lambda perturbation theory, you get F1 of lambda. But if you work in the large n limit, you only care about the sphere diagrams. Everything else is suppressed by powers of 1 over n squared. So you can throw away, in the large n limit, an infinite number of Feynman diagrams. Of course, you get left with an infinite number of, you still have a non-trivial infinite number of them, because you still have to draw all the diagrams that you can draw on the sphere. But this simplifies perturbation theory. And I think you probably won't see string perturbation theory in your 2 courses, but the analogy with string perturbation theory is quite accurate here, because string perturbation theory also is organized as a genus expansion, with string loops being drawn as world sheets with higher genus surfaces. So people have long speculated, Toft himself in the early 70s, that there must be a string theory underlying large n gauge theories. Because people have, and one intuition for that is simply that in Yang-Mills theory, which confines, non-supersymmetric Yang-Mills theory, which actually confines, the right degrees of freedom are not the gluons. If I just take pure Yang-Mills, the correct degrees of freedom at low energies are not gluons. They're glue balls, but the way to think about the glue balls is you can think of them as sort of built out of flux tubes of gluons. So people have speculated that really the right way to reformulate just ordinary QCD at large n is in terms of flux tubes, and the classical theory of those flux tubes is like some string theory with this genus expansion. Okay? Now there's some interesting piece of work which has been done in the last couple of years by people like Ofer Aharoni and friends, and by Sergei Dubovsky and friends, who've been trying to compare lattice data for SU4, SU5, SU6. Lattice data exists up to SU8 with what I would call a macroscopic string theory, not a microscopic string theory that like what you're learning in your course, but a sort of effective field theory. And it works very, very well. It's actually quite amazing how well it works. It's a phenomenological modeling, trying to understand what you see in the data, what the data in the lattice are telling you about the features of this effective field theory. It's a bit, if the analogy is, which is most accurate here, is a bit like trying to describe physics of pions. Before QCD was invented, people understood a pion physics in terms of what's called the chiral model, which is just like an ON sigma model. And so the claim is that there is a sigma model, which is the sigma model of these strings, string-like objects, flux tubes, which has this. I mean, it clearly has this kind of expansion, and this expansion can be fitted against lattice data to see what are the coupling constants of that effective field theory. But for our purposes, all I want you to take away here is that large n simplifies things, and it zeroes in onto the sphere level correlators, which means that to some extent I would call this the sphere diagrams dominate, and I would call this the tree level approximation. Because all the loops which come from the handles that you can draw on the which give you the higher genus surfaces. And this is sort of clear from this picture. The action, our Lagrangian, went like n over lambda times trace f squared, which means that in the action I have n over h bar lambda, So h bar is like 1 over n in the theory. Because if I compare where n appears and where h bar should appear, it's telling me that 1 over n effects are like h bar effects. Okay? So perturbation theory is natural, and so the effective h bar, maybe it's best to write it that way, is h bar over n. So if you like, what's really happening in the large N theory is that the quantum effects are being suppressed by powers of n. So there's a very, if you're interested in this, I refer you to a very nice review written by Larry Yaffe in early 80s, 81 or 82, where he discusses various simple large N models and shows that they all behave classically by making explicit contact between large N theories and classical limits. So going back to the question I was asked earlier, this is sort of the rough intuition. N controls h bar effects. So you want n to be large for quantum effects to be small. And the mapping in the ADS-CFT takes n to 1 over G string. So it sort of fits in very nicely. So string interactions are like h bar effects in the string, and they are suppressed if you take n large. Okay? So for ADS-CFT, G string is 1 over n. So you get suppression of string loops. And just on a philosophical note, although Tooft expected that large N gauge theories, even QCD, would simplify to give you string theory, we don't yet know what the true string dual of QCD is. All Tooft said was that there is some classical theory. And that's sort of what we are finding by doing this counting. What ADS-CFT says is something very, very strong. It says that for a class of theories which are not QCD, but they're related to QCD, like n equals 4 Yang-Mills, or theories that come out of string theory, we can tell what the answer is, what the classical theory is. Okay? So the other way to interpret ADS-CFT is that ADS-CFT gives us the answer to the question, what classical theory describes large N limit of, say, n equals 4 Yang-Mills or related theories. So we just Maldasena's insight here was to just hand us the answer to this question by thinking about the structures one sees in the deviant context. Right? Any questions?
So what's the procedure of first having a gauge theory and then looking for the classical theory?
What's the procedure?
Yeah, because you showed us that, let's take the two links and put them together, and then we find this and then we close it.
Yeah.
But so like if I come to you and say, oh, I have a gauge theory,
Yeah.
can you help me find an appropriate?
Holographic duo, appropriate classical theory.
Yeah.
Yeah.
Should I interpret the statement as this ADS-CFT framework
Okay, I'll answer your question at two levels. So there's one level of answer, which is what I was going to describe later today, which is to give a phenomenological answer. You give me a gauge theory, I look at all the symmetry properties, all the symmetries it has, global symmetries it has, kind of fields, operator content it has, and try to model some theory which has those properties. Okay? And I will use a lot of intuition from ADS-CFT, which says that the classical theory is not really a classical theory without gravity, it's a classical theory with gravity. It's some kind of string theory in some higher dimensional space. So I'll just cook up something based on the symmetry intuition that I know, and I know how ADS-CFT works. That's an answer, but it's clearly phenomenological. It's not a derivation. The real question you're asking is, can I do a derivation? And the answer is no, because see, the amazing fact about this statement is that someone just pulled out an answer and gave it to you. And we haven't derived ADS-CFT at this fundamental level to know why it does this. And to some extent, I think that there's a sort of philosophical question here, which is, how do I say this? It's a bit of a chicken and egg problem. What is fundamental? So n equals 4 super Young Mills, I write down some Lagrangian for you. It has gluons, it has gauge fields, it has adjoint matter, etc., etc. But somehow all those degrees of freedom have to reorganize themselves in terms of some completely different variables, which are gravitational variables or stringy variables or what have you. And we need to see equivalence at this level. But think of any other kind of duality, So think of electromagnetic duality. On one side I have electric degrees of freedom, on the other side I have magnetic degrees of freedom. Are they related by some simple map? Not really. I mean, you can write down some classical map that looks like they're related by some simple relation. But it's very hard to see in the electric theory what the magnetic degrees of freedom are, and in the magnetic theory why the electric degrees of freedom are. So what we can compare independently is we can compare invariants on both sides. So the proof to the sort of the easy level of the proof, which is to say, you write down some model, and then you do computations on both sides and check that they give you the same answer for the same physical quantities. But that depends on getting the dictionary right. Okay, so we're filling out some elements of the dictionary, we need to fill out some more. But there's a second level of answer which says, take one description and do a set of well-defined mathematical transformations on it and get the second description. We've been looking for 20 years. We don't know how to do this yet. Maybe you guys will help us. My feeling is that should be possible. We just don't know how to do it. Okay? But it has to be done in some clever fashion. It's not some naive trick that you can say, oh, let me just implement a set of rules, and I will go from this n equals for super Young Mills to string theory. Yeah. I mean, the facetious answer here is, it's like in the Hitchhiker's Guide. You know the answer is 42, but what's the question? Okay, so that ends philosophy session. So, okay. So let me say one thing, that we were talking about operators in the field theory. So in large N, the operators of the field theory should also be organized correctly. And let me write a few operators. Let me just keep pretending I have only a Maxwell field. sorry, what am I saying? A gauge field. So I can have operators like this, where I have a string of f's, and then I take a trace. Okay? So these are called single trace operators because they have one trace. On the other hand, you can also have operators like this. Where I take two independent traces and multiply them. That's also an operator in the theory. It also is gauge invariant. So this is a double trace operator. It has two traces. And so you can have multi-trace operators. At finite n, the trace basis breaks down when we have order n operators inside the trace. Order n fields inside the trace. Right? This is clear. This is just matrix algebra. If I have n by n matrices, trace m squared, trace m cubed, up to trace m to the n minus 1 are independent because they're just sum of eigenvalues, sum of square of eigenvalues, sum of n minus 1th power of eigenvalues. But eigenvalues satisfy a polynomial equation of order of degree n. So trace m to the n is no longer independent. There's a trace relation. It's determined in terms of these guys. Okay. So the multi-trace operators break down at some point if you have when you hit n objects inside the trace. But we are doing something funny here. We're taking n to infinity. So we are sort of separating the single traces from multi-traces. The trace basis stays good for a long time. But what happens at some point is that it's still useful a determinant basis when we have order n operators, when we have order n fields. Always write traces in terms of determinants. This is a simple relation because again they're both functions of eigenvalues, so you know how to go between them. So the reason to bring this up is the following. I told you that fields in ADS yeah. Not necessarily. No, because you see, we could have an energy momentum tensor operator in the Yang-Mills theory. So T mu nu will be trace So, because operators don't have to be Lorentz scalars. If you want to stick operators into Lagrangians, they have to multiply them with the right Lorentz structure to make scalar densities, but operators themselves can be whatever they are. So as we said yesterday, remember that operators come with a set of quantum numbers, which are described by, in conformal field theories, by their conformal dimension and their spins. But all we are doing, in addition to the discussion, is segregating them based on how many traces they have. Because we're keeping track of powers of n, which is a finer distinction than we were trying to do yesterday. So we were trying to say that classical fields in ADS correspond to operators. The correct statement is these correspond to single trace operators of the dual field theory. Okay. Double trace operators, multi-trace operators, in the field theory are more like multi-particle states. In the bulk. When the conformal dimension of the operator becomes order n, this mapping breaks down. Operators with scaling dimension of order n are D-brane states in the bulk. So I started by saying various things about D-branes when we did classical gravity, but even the classical theory, it's still a classical string theory. So if you ask sufficiently complicated questions, by asking for operators whose conformal dimension also grows with n, you start seeing the fact that you're doing string theory. You're not doing classical gravity anymore. These are non-perturbative. They're non-perturbative in the 1 over n expansion, because, and that's roughly what you expect. So the D-branes are soliton states. So they behave like 1 over h bar, and the 1 over h bar is coming from this n. Okay, so that's a aside. I'll just to be clear, we will be interested in. So depending on how far we get today, we will be interested soon in states whose energy goes like n squared, even, and you'll see why in a second. And they are classical and not classical at the same time. So when we talk about black holes in ADS-CFT, they will correspond to states whose energy goes like n squared. Any questions? So is this large n story clear? So hopefully you get a picture. And I sort of done this for the gauge theory where things are reasonably simple, the n counting is straightforward. But there's a sort of abstract way to say this, which I like a bit better. And let me just say it, because it unifies many different ADS-CFT dual pairs. So large n for gauge theories can be rephrased as large central charge and I'll call this C effective. So for gauge theory, C effective scales like n squared. Okay. But we might have other ADS-CFT dual pairs, like 2D conformal field theories being dual to string theory in ADS3. And the 2D conformal field theories don't have any gauge degrees of freedom, they don't have gluons, but they have a notion of a central charge, like you know, from string theory. So if you want to ask which two-dimensional conformal field theories have nice semi-classical duals, they are the two-dimensional conformal field theories that have large central charge. Okay. So it's a more invariant way to talk about central charge instead of this n counting, although people understand them sort of isomorphically. So I'm skirting over one technical point here. I should, strictly speaking, define the central charge for you. I'm going to define it for you in a while when I talk about black holes and thermal states. As you can think of the central charge the number of degrees of freedom obtained from the free energy. Okay. But just to be sort of keep my disclaimer correct, there are other central charges. There are multiple central charges in higher dimensional field theories. And they are determined from the conformal anomaly. So in 2D, the conformal anomaly is the statement that when I take my conformal field theory and put it on a curved space-time, the energy, so conformal invariance forbids a trace for the energy momentum tensor, but if you put your theory on a curved background in presence of an external source, the energy momentum tensor picks up a expectation value, which goes like the Ricci scalar of the background and so on flat space you won't see this because the Ricci scalar vanishes, but if you put your conformal field theory on a two-sphere you will see this because the two-sphere has constant Ricci curvature, and so you'll see a central charge contribution. It's like a vacuum energy. It's what you see in string theory. But in 4 dimensions, the same thing happens, except that now there's an A central charge that couples to the analog of R, which is a quantity I will write as E4. It's the Euler character Gauss-Bonnet invariant. And there's another quantity which people call C, which I will call W4. It talks to the Weil squared of the background. So A and C are 2 central charges. E4, so this is the first, is the Euler character of a two manifold, integral R. Yeah, so there's an analogous object which is Riemann. It's a, okay, so E4 is this gadget. Is what it was Bonnet invariant, so E4 is. I think this doesn't have a 4, but double check. I'm sure of this sign, not sure whether it's a factor. So it's another topological invariant for 4 manifolds. W4 is some particular contraction of Weil tensors. Actually, maybe just there's only one contraction, just 2 Weil tensors, right? So it's just. N to the minus 1. In the large n limit? No. Well, depends what we mean. Let's see. So we know something about unitary conformal field theories in 2 dimensions. Let me not talk about 4 dimensions. 4 dimensions is more complicated. So in 2 dimensions, C is positive, first of all, for unitarity. And unitarity also says that if C is less than 1, it comes in a discrete family. Okay? So Virasoro minimal models pick out discrete values of C that lie between 0 and 1. For C bigger than 1, there are some theories that you can classify, but generally there's no classification. But the rough statement here, you should think of C. It's not a very good analogy. People like to state this statement, but this statement comes with a set of caveats, which I won't go into. You should think of C as the number of degrees of freedom. So if you have an intuition that you have n degrees of freedom, she should somehow scale with n. So okay. So all I wanted to say here was that in 2 dimensions, this C effective is really the central charge. Okay, up to some maybe trivial rescaling by some factors of numerical factors. In 4 dimensions, this C effective, you could relate it to either of these, but it's not really either of these, what I'm using. Okay. But I will unambiguously define it in terms of the free energy. So let's just leave it at that. Okay, so we've now clarified our statement about the fields. I now want to do the following. I want to make a slightly abstract discussion about the data. So we have let's say we work at large central charge, and the quantum field theory, the conformal field theory is at strong coupling. So in this sort of phenomenological picture I was trying to describe a while ago, we can think of the bulk dual, bulk ADS theory. I will write as I'll take the bulk theory to be the simple theory, which is Einstein-Hilbert with a negative cosmological constant and some matter. Okay? What matter will depend on what question I ask. So if I'm interested in some particular question, I might not have to worry about full Lagrange, and I might be able to truncate it to some simple setup. Okay? So for n equals 4 super Yang-Mills, S bulk is a described by type 2b supergravity on ADS 5 times S5 in this limit. Okay. Since S5 is compact, we can decompose fields in spherical harmonics and write down effective 5D theory with an infinite tower of fields. I call it the Klein tower on ADS5. With that understanding, I've always truncated my to be this Einstein-Hilbert in 5 dimensions times some other stuff, with some other stuff. So if you're wondering what kind of stuff does this theory have, 2B Sugra has 10D metric, it has 10D NSNS2 form, it has a dilaton, it has an axion, it has a Ramond-Ramond 2 form, a Ramond-Ramond 4 form which is self-dual, and it has fermions. There's Gravitini and other stuff. The bosonic content is this lot. There's some action you can look this up. Polchinski has it, or Thomas Ortin's book on supergravity has it. There's a very explicit action that was constructed by supersymmetry analysis long time ago, and you can take that action, do this harmonic decomposition, and write the theory this way. Okay, so the one thing to note is that the 5-dimensional Newton's constant, rather 1 over 16 pi times the Newton's constant in 5 dimensions, is the volume of the phi sphere divided by the 10-dimensional Newton's constant. Right. So if you want to compare what parameters you get, you have to make sure that you get this, account for this extra volume factor. Because I'm assuming modes are, I'm just decomposing on the internal space. And that's correct because this guy scales like length cubed, this guy scales like length to the power 8, so I need to kill 5 powers of length by accounting for the volume. So let me make the following observation. Say that your favorite ADS-CFT theory, you've sort of worked out something like this, say for type 2b supergravity. We've written down this action. Okay? And so far what we've been trying to do is talk about physics in ADS spacetime. I've told you how Klein-Gordon fields, I solved the Klein-Gordon equation in ADS spacetime. Now I want to do a bit more than that. So I want to answer the following question. So what can we do with this structure? So pictorially, we can draw the geometry as we were drawing before. And what we have is the data are the boundary conditions I need to give you. At the time like infinity of ADS. And let me state the problem as follows. So take conformal field theory D on some Lorentzian manifold which I will call B. So B is the boundary. So far we only talked about Minkowski space or this Einstein static universe, but now I'm just going to generalize. I'm going to take my conformal field theory and feel free to put it on any background geometry. We can study field theories on whatever background space-time we like. So let me do that and prescribe sources for various operators of interest. Let me collectively call that JO. Okay. So the metric on BD is the source for the energy momentum tensor. Now given this, I can ask you what is the geometric description in the bulk of my field theory with all these parameters described, given to you. Okay. The ground state of the quantum field theory with this data is obtained by solving the equation of motion from S bulk subject to given boundary condition. And demanding regularity everywhere. Okay. So if I give you all this data, your job is to try to solve the equations of motion that come out of here, which are Einstein's equations coupled to various matter. Find some metric in the bulk, find configuration of fields in the bulk, which is smooth everywhere. Smooth everywhere in a sense, with a qualifier that it has to be smooth in the part of the bulk that can communicate to the boundary. You can have black holes, and you can have black hole singularities as long as they're hidden behind horizons. Okay? So that's the task. That's how the theory is with these boundary conditions. That's the geometric way of encoding this particular configuration of the conformal field theory. And once you have this, you can then ask for correlation functions of the theory around the ground state of this configuration. So we already solved the easy problem. For the boundary manifold being Minkowski space, and no sources, dual geometries Poincare patch of ADS, for the boundary geometry being the Einstein static universe and no sources, the dual geometries global area spacetime. But these are just two examples. You can choose some other boundary geometry. You can turn on sources, and you're left with the pleasant and happy task of solving Einstein's equations. Maybe easy, maybe not easy, depending on the symmetries of the game. So I talked about ground states. Similar statements hold for excited states. Not all states, however, will have semi-classical gravity duals, or maybe I'll just say classical gravity duals. It may be that you try to solve the equations in this for this. So let me call this bulk n plus 1. It may be that you try to solve the equations of Einstein's equations and try to find the geometry in the bulk, and you get a singular answer. You get some singularities. Fields blow up somewhere. All that means is not that the field theory is doing something bad. It just means that the classical approximation is not good for describing those states. Okay. So for excited states, the class if this doesn't happen, this just implies that these have to be thought about in the microscopic string theory. And the question of which states admit nice classical duals is an open question. People are trying to actively think about this. And there's a conjecture, which I will flesh out for you once I talk a bit about some new things like entanglement entropy. Okay? But at some basic level, you have a well-defined set of partial differential equations to solve if you want to understand probabilities of a quantum field theory, which you know to have a holographic dual with various data of this kind. So what ADS-CFT is really good at is providing answers to complicated field theory questions. Is this clear? I was going to describe some examples for you, but is the general philosophy clear? The bulk fields have to obey these boundary conditions for the sources. I already told you what the asymptotics of the fields, for some fields I already told you what the asymptotics should be. So maybe I should have been clear. Okay. They will diverge, but they will diverge in a prescribed manner. But let me just clarify this by saying the following. The bulk solution is an asymptotically locally so as I go towards infinity, the fields should behave like ADS spacetime with small corrections. So if I introduce a coordinate z here, there is a Taylor series expansion for the metric at small z. This is called the Pfefferman-Graham expansion. And for example, the bulk metric behaves as so gamma mu nu is the metric on BD. And then there's a power series correction here. Where gamma k bar is a functional of gamma and the Christoffel connection on gamma. So you can determine these gamma k's by, so let me call this gamma 2k. You can determine this in terms of metric and the curvatures of gamma. This you can do explicitly. Okay? So gamma 1, for example, gamma bar 1 is given in terms of this combination of the curvatures of the metric gamma. But this is not complete. There's an ambiguity. Where should I write this? Let me erase this for a second. I'll rewrite this equation. Let me say it this way, plus some homogeneous piece. It starts out its life at order z to the d. I'm being a bit schematic here. This expansion is fine up to some order, and then the secular terms that are undetermined by the asymptotic series. So if you know differential equations, if you try to solve second order differential equations, sometimes you find that there's two solution branches, but there's an undetermined set of second asymptotic expansion which starts with a new undetermined coefficient. It's a bit like that. So you started out an asymptotic expansion given gamma, which was one set of boundary conditions, but there's a second allowed expansion term which you have to determine some other way. This is just a statement that what I've done here is prescribe for you boundary conditions for a second order differential equation at infinity. But that's just one boundary condition. So you can't solve the problem uniquely with that boundary condition. I need two boundary data to solve a second order differential equation. So this is that ambiguity. The claim, this is the hard part, this is what makes this problem very hard, is if you solve the equations and demand regularity, that regularity will fix this given this. So it's not enough to do the Taylor series expansion to solve the bulk geometry. You actually have to solve Einstein's equations explicitly to make sure that you know the geometry everywhere. So this Pfefferman-Graham expansion is good to know what things look like near infinity, and there the question you asked has a sensible answer. Things have a definite fall off which you can determine analytically because it's just doing perturbations around an ADS spacetime. But you unfortunately don't get anything for free out of it. You actually have to go solve Einstein's equations later. Okay. And I will say one more thing, that this expansion, the first line of this expansion is fine across dimensions. It jumps in powers of 2. You can show that. This line is a bit funny because there's a logarithm. There's a logarithmic singularity for d being even. Okay. This is very crucial. It's related to the physics of the conformal anomaly I just talked about a while ago. But let me not go into that discussion for now. Okay. So in odd d, there's a Taylor expansion in powers of z. In even d, there's a Taylor expansion in powers of z plus a new series with a log. The log also is easy to understand from differential equation perspective. When you solve second order equations, you write down a characteristic polynomial which tells you what the initial solutions are for the Frobenius expansion. When the initial roots coincide, you're allowed a solution branch with a logarithm. So that's the origin of that in even dimensions. Okay, so I won't use this very much, but there's a vast amount of literature on doing this. I refer you to Kostas Kenderis' papers on holographic renormalization, where he will go through this in gory detail. They have a nice paper. The review-like paper is by De Haro, Skenderis, and Solodukin from 2000, 2001. But I should say that Pfefferman and Graham did this for a completely different reason in the 80s. They were interested in properties of conformal manifolds. They are mathematicians. And so they realized that they can study conformal properties of D manifolds by embedding them in one higher dimensional ADI spacetime. I mean, we want to do more. We want to study conformal field theories. They wanted to study geometries of differential geometry of manifolds with a conformal structure. All right, so here are some examples of this philosophy. So I already told you two examples, which are sort of the easy ones, easy things to state for two different boundary matrix, no sources. We can also find, so of course, I've given you the general philosophy. I'm not going to write down lots of matrix, simply because most of these matrices are not analytic. So, most often if you want to put down some source, it's very hard to write down an analytic geometry in the bulk, which solves Einstein's equations for metric and the fields. But we can solve them numerically. So a lot of effort in recent years has been on trying to understand properties of quantum field theories by numerically solving Einstein's equations. And so some very well-developed algorithms to study Einstein's equations numerically in ADS spacetimes. Okay. But let's talk about some special cases, which are easier to state. So one example I like is the following. So let's take the following. Let's talk about a state of the conformal field theory, which is a coherent excitation of a single trace operator. Okay, so this is O has some weight delta. So what I'm imagining is that I want to take this guy and act on it. This is the vacuum state, and I want to act on it with various creation operators corresponding. I want to think of O as a creation operator, and I want to act on the vacuum with this creation operator. And if I act with it k times, the dimension, the energy of the state, or the conformal dimension of the state, scales like k times delta. The dimensions are additive. Now I want to ask, can this state have a gravitational dual? Can I write down a geometry dual to this state? And let's understand what that statement means. So what I really want is in this state, which I'm calling k. What I know is that k t mu nu k is of order k delta, and k OK is non-zero. Right? Because this guy is a 2k plus 1 point function, which doesn't have to be 0. So in the vacuum, conformal invariance says that, or even Lorentz symmetry will tell you that for most operators, 0 O0 vanishes, but in an excited state, various operators can have 1-point functions. So we just got the energy, but even the operator O will have 1-point function. And let me pretend for now that this operator only talks to the energy momentum tensor, it doesn't talk to anything else. So no such operator exists generically, but let's make that approximation to understand what the geometry would be like. Okay? Is that clear? So what are we learning? We are learning. Oh, and let me fix the my formalism. I have to also tell you the boundary metric. Let me fix the boundary metric to be Minkowski metric for simplicity. So I've kept flat space, but then I have turned on these guys. Actually, no. Let me not do this. It will be harder to explain regularity here, so let's do this. Let's take it to be on the sphere. So clearly the fact that I can act with many O's in the state means that O is bosonic. O was fermionic. I would not be able to act with it multiple times. So let's see. So I'm going to try to solve Einstein's equations for this S bulk. Since I have one operator O, I know that I should have a scalar field phi maybe with some interactions. But let me try to truncate it to this massive scalar field, and let's ask what, in this toy model, what things look like. So mass, of course, is determined by delta. So what we can say is the following: if there is a geometry corresponding to such a state, we should have some metric which I will parameterize as follows. Oh, assuming that we retain spherical symmetry. That is, when I act with these operators, they're scalar operators, I smear them on the sphere so that I get a homogeneous state. I get a state that's not, I don't have operators sitting at various points. I get something homogeneous on the sphere, on the boundary. So state doesn't break. All the state does is it has energy, so it breaks the Lorentz symmetries. It's an excited state. Only the vacuum preserves the full Lorentz symmetry, but it preserves the spherical symmetry. So the metric only has it differs from it. It has a time translation. It's a static state, and it's an energy eigenstate, and it has spherical symmetry. And this is scalar field phi is non-zero. So now you can basically do the following. You can take these two as your ansatz, plug them into the Einstein's equations you get out of this action, and try to solve them. And you will solve them subject to the following two boundary conditions. Where asymptotically, as switched coordinates, r is going to infinity at the boundary of ADS. F of r should go like r squared. G of r should go like 1 r squared, because compare with the ADS metric in global coordinates, and phi of r, well, what should phi of r do? It has these two fall-offs. Which one should I pick? Sorry? Phi is a wave. So in this case, we are only acting with the operator on the vacuum, so we are building an excited state. We are not turning on a source for phi. I don't have some classical field that's throwing out phi particles into the state. There's a unique state. So phi should asymptote to the normalizable solution, which is z to the delta, which is 1 over r to the delta plus, at infinity. So you know the asymptotic boundary conditions. You know how fields are behaving as they go towards infinity. That's one set of boundary conditions. And you say phi of r and f of r and g of r are smooth functions of r. You have ODEs now, because all the functions depend on one variable. Einstein's equations are just ordinary differential equations. We can write them down. I won't write them down for you. But you can immediately solve these equations and realize that what happens is the following. The field phi starts out, so this is the radial coordinate, this is phi of r. The field phi starts out at some value phi 0 at the origin, and then has some profile. It decays down to infinity with the right fall off. And you can see that there's only one parameter in the game, which is the value of phi at the origin, which determines what the asymptotic fall off piece is. So the wave is a function of phi 0, and Einstein's equations then tell you what g of r and f of r are as functions, and how is the energy determined in terms of phi 0. Okay? So all of these you can just solve and get some expressions for the quantities. But the key thing I want you to note is the following. The energy, I'll say this and then stop. It's getting close to lunchtime. So the energy in the scalar field can be determined at infinity which gives you the boundary stress tensor. But this guy is proportional to this wave but it's also proportional to 1 over 16 pi g Newton, because 1 over 16 pi g Newton is sitting in front of the action. The ADM energy of the solution cares about what the Newton's constant is. So we need for these functions to be non-trivial, we need the energies to be of order 1 over g Newton, but energies of order 1 over g Newton, if you use the relation between various quantities, means that there are the energies of order n squared. So states with energies of order 1, order n, they are not classical in this sense. The geometry is just the ADS geometry, if you fix the background and don't turn on sources, with sprinkling of one particle or few particle states in the bulk. If you want to build up a coherent state which non-trivially differs, where there's some scalar field which has some profile, the geometry is non-trivially different from the ADS geometry, then we need macroscopically large amounts of energy. Okay? And this is, you might call this, some people like to call this a boson star. I should have been a bit more specific here. This is properly accurate for a complex scalar. It's not quite accurate for a real scalar. A real scalar will oscillate in time. But all right, so I think that's all I wanted to say. So you can build geometries of this kind. We can do other things. So tomorrow we will see one example. We'll start with an example of trying to understand how to think of not a state created by a single operator, but how to think of a thermal state of the field theory and how they're related to the physics of black holes. Okay, I'll stop there for the day.